Okay, and probably the toughest of the grouping that I assigned for the homework this week was 3.10, number 36. This one's going to take us a little while to figure out here. Two cylindrical pools are filling simultaneously at the same rate in meters cubed per minute. The smaller pool has a radius of 5 meters, and the water level rises at a rate of 0.5 meters per minute. The larger pool has a radius of 8 meters. How fast is the water level rising in the larger pool? I want to see if there's any other information that they give us on this one. And it looks like that is about it. It just says the inflow rates are equal. So, one of the things that you'd want to try to do on something like this is maybe see if you could draw a rough sketch of what this thing looks like. So you got a pool here, okay? And you've got a smaller pool over here, like this. And we've got something that's filling them, but it winds up filling them at the same rate, even though it doesn't look like it does. It's filling them at the same rate. Okay, so they essentially get the same amount of water filling these two. Now this one here had a radius of 8 meters, and this one here had a radius of 5 meters. So this gives us what's going on with these pools. So they're starting to fill up with water in here. Okay, it's pretty obvious that as you look at this, the one with the smaller radius, if we're sending the same amount of water in there, it's going to rise faster, right? So we're going to expect, if this is rising at a half meter per minute, it's pretty obvious that this one's not, right? That it's going to be rising at a slower rate than the other one. So a couple of things that we'd want to do. So I always look to the front of my book and say, well, what shape are these? Well, they're cylinders. And as I look to the front of my book here, kind of seeing here, it's volume is pi r squared h. So for a cylinder, so we can say for a cylinder that volume, and I'll just write of a cylinder. And you know what? I'm going to take that back here. I'm going to say volume of the, because I think we've got this. We've got more information for the smaller pool. So I'm going to say the volume of the smaller pool is more important to me at this point. So I'm going to say volume of the small is again equal. I got to look at the front again here. It's pi r squared h. So pi r squared h, and by the way, that is the area formula. So in 2 dimensions, we only care about pi r squared. We add that third dimension, we have to multiply by h. So the volume of the small, we can actually, I think we can work with this. So what are we doing with this though? We don't know what the height is at any given point, do we? So we can't really solve for this. We don't know the volume, we don't know the height. But what we do know that's kind of interesting is we do know that the volume is changing with respect to the height. So I might even say something like dv dt, okay, or the change in volume with respect to time is going to be equal to pi times r squared. I do have the r at 5, so that's pi times 25. And the change in volume with respect to time is a function of the change in height with respect to time. So those are both derivatives. However, what's interesting thing here is I do know this change in height. So again, we're talking about the small one here. I do know the change in height with respect to time. The change in height with respect to time was 0.5 meters per minute. So that's kind of interesting. So dv dt of the small one would be equal to 25 pi times 0.5. Or dv dt, I could simplify that a little bit and say it's equal to 12.5, because it's volume, 12.5 pi, 0.5 times 25, meters cubed per minute. That's the change Now what's interesting here though, that's the change in volume for this change in height. We've got the same change in volume for this pool, although the height is going up slower. We still are going to have the same change in volume. So that's actually an interesting note here. I'm going to change my pointer here, give me a different color here, and we're going to call this the large pool over here. So this will be the large pool that we're calculating right now. And so the volume of the large, we could say, yeah, we'll go with the volume of the large. Well, it's the same equation. It's pi r squared times h, so that's the same exact equation. The dv dt, though, that doesn't change. That's still this, because I'm filling at the same rate. So the dv dt of the large is still 12.5 meters cubed per minute. That didn't change. I'm still, if you think of it as adding milk jugs of liquid to each pool. Well, if I'm adding the same amount of milk jugs, I'm adding the same volume to each pool. One is just getting spread out more, and the other one's getting spread out less. So that's not a big deal. But the dv dt of the large one, is also with respect to the it's a function of the height also. So dv dt, just like this one over here, is now going to be equal to 8 squared, because r squared is now going to be 8 squared, which is 64 pi, times a function of the height, dh dt. Oh, here's the interesting thing though. Look what we just did. dv dt, we know now. So 12.5, and I've told you guys this many times, I'm not as big a stickler for units as I should be. When you get into your physics courses, physicists tend to be much greater sticklers for the units. Equals 64 pi times dh dt. dh dt is the rate at which the height is changing with respect to time. Well, now this is a simple pre-calculus dilemma. No big deal here. So what I'm going to do is I'm going to take that 64 pi, take 12.5 and divide by 64 pi. 12.5. Oh, let's see here. Ooh, I got to be careful here. Something got messed up right here. This should be 12.5 pi. So I need to change this dv dt slightly. Sorry about that. Something looked goofy there. So that should be a 12.5. Oh, I'm going to erase one more time here too. Should be a 12.5 pi in both those locations. Pointer options, pen. So that's a 12.5 pi. And this is a 12.5 pi. Very nice, because now this divides out much simpler. We can say dh dt, the change in height with respect to time, is 12.5 pi divided by 64 pi. The pi's just cancel out here, so those just go away. And I get 12.5 over 64. I could double that and say that's 25 over 128. Because we're talking about rising height, it would be meters per minute. That would be the rate at which that one's rising. Now, my gut check, I always want to do a gut check and say, does this even make sense? I knew this one over here was rising at, that's the volume change. Oh, here it is. This one up here was rising at 0.5 meters per minute. What is 25 divided by 128? Well, it's about 1/5, so it's about 0.2. So this would be rising at, lose my pen here. This one here is rising at about 0. Is that right? 25 times 5, yeah, so about 0.2 meters per minute. So it's less than half. Well, that makes sense, right? Because this is a much larger pool, so it's spreading out much greater. So 3.10, again, number 36, what you really have to do is kind of dabble with all the, You know what's interesting here is we never actually took a derivative in this problem. We used the derivative, the rate of change of the volume over here and the rate of change of the height, but we never actually had to take a derivative to solve this one. So that's a little bit interesting.